All right, so I'm going to make this a two-part video. Part one going to be going over the concept and the main idea, and then part two is going to be going over examples. So section 2.1 deals with the what a derivative is and the tangent line problem. And in one of the earlier videos, I briefly went over the tangent line problem, so now it's just going to go over it again, but in more specific detail. So the idea is you have a tangent line to some curve f, and so and that tangent line I'm showing as the red line. And all a tangent line means is it touches the curve at a single point. And then in this case, the single point is P. And the question we're asking is, how do we find the slope of this tangent line? So recall that slope requires knowing 2 points. M is equal to y2 minus y1 over x2 minus x1 for the points x1, y1, x2, y2. So we're left with a problem here because tangent line only touches the curve at one point, but if we're trying to find the slope of that tangent line at the curve at that point that it touches, how do we find the slope when the slope requires knowing 2 points? And the answer relies on a limit process involving secant lines. And a secant line is a line that touches the curve at 2 points. That's what a secant line means. And so I drew this picture right here. You have this red line's the tangent line, and then the green line's a secant line. And it's supposed to go through the 2 points P and Q. Now the thing is, we're going to keep the point P fixed, and the point Q is going to vary. And the idea is the closer Q gets to P, so if we get point Q approaching point P, the better the approximation will be for the slope of the secant line. So we're going to use a secant line to approximate a tangent line, because the secant line gives you 2 points, and those 2 points you can plug in the slope formula. And the thing is, we're going to keep P fixed at its stationary, and the point Q is going to change, and it's going to get closer and closer to P. So I can make it closer and closer to P. I could put Q right there, Q right there, and then if you find the slopes of these of the line that goes through these varying Qs, it's going to be closer and closer to the slope of the red line, the tangent line. So you'll see from just comparison in this one on the bottom right, I have Q's closer to P, and the green line is closer to resembling the red line. Whereas for here, my original drawing, I had Q up here, and the green line does not match the red line as close as this one does. So the idea is the closer I get point Q to P, the better the approximation will be for the secant line mirroring the tangent line. And by mirroring, I mean the slope of that green line being equal to the slope of the red line. And so I wrote it in shorthand notation as Q and then arrow P. That means as Q approaches P, and then M, and it's got a subscript SEC for secant. So M's the letter we use for slope. So the slope of the secant line, and then approaches slope of the tangent line. That's the idea. As Q approaches P, the slope of the secant lines approach the slope of the tangent line. And this is a specific type of limit. And so to formalize all this, we're going to let P be represented by the coordinates C, comma, f of C. Recall that if you have x, comma, y, you can represent it as a point as x, comma, f of x. All right, f of x is the same thing as y. So y equals f of x. That's just function notation. So for the x coordinate c, that's for a point P, the y coordinates f of c. So I'm going to let h be the horizontal distance away from the x coordinate of P. And so this point Q is going to be represented by the coordinate c plus h. So it's the x coordinate of x coordinate of P plus this horizontal distance, and then the y coordinate of that value when you plug it into the function. And so graphically, it'll look like this. So you see you have P, the point P in blue, and I put point Q in purple. And the point P's got x coordinate c, y coordinate f of c. And if I were going to the right of c, a distance of h units, so the difference between c plus h and c is a difference of h. So starting at c, go to the right h units, I end up at c plus h. All right, and that's the x coordinate for point Q. Its y coordinate is f of c plus h, since that's what you plug into the function c plus h to get the y coordinate. All right, this is just formalizing everything what we were talking about before. So when I was saying as q approaches p, that is the same thing as saying as the distance h approaches 0. The slope of the secant lines approach the slope of the tangent line. So the closer q gets to p, the smaller this distance is going to be. And I'm just using that distance as the letter h. So in words, I wrote, as the horizontal distance h shrinks to 0, the slopes of the secant lines from P to Q get closer and closer to the slope of the tangent line at point P. And then we could use our slope formula, where m is equal to y2 minus y1 over x2 minus x1, and write it as the definition being slope of the tangent line is equal to the limit lim, and then h goes to 0. So that's the horizontal distance shrinking to 0 of f of c plus h. That's the y coordinate of q, minus f of c. F of c is the y coordinate of p. And then c plus h is the x coordinate of point q, and then minus c is the x coordinate of p. So this f of c plus h portion, this is like our y2. Our f of c is like our y1 according to slope. C plus h is like x2, and then c is like x1. So it's got that formula structure of slope. And if you notice that c and minus c are going to cancel out. So I can go ahead and cancel these, which leads me to the following. So this is and I put this boxed, so this is the official definition of slope of tangent line at a point where its x coordinate is c and the y coordinates f of c. So m tan, that's slope of tangent line, equals limit h goes to 0, and it's f of c plus h minus f of c divided by h. So it's really just what I had above. So it's really this, but the c's canceled out. All right, and that's a key definition you should write down that we will be using in the examples. All right, so just to go over real quick, we're formalizing this process that the secant lines between point P and Q, if I were to make point Q get closer and closer to point P, that means the distance between the x coordinates of the 2 points, which I'm calling h, is shrinking to 0. So in this case, point Q is represented by c plus h for its x coordinate, where h is this distance cr from c. So if that distance c plus h goes to 0, that's like doing c plus some really small number, c, and it's getting closer and closer to point P. So the green line, if I make Q get closer and closer to P, it will eventually mirror the red line, the tangent line. And that's how we can get the slope of a tangent line, is using a limit process involving secant lines. And that limit process is saying as h approaches 0, the slope of the secant lines approach the slope of the tangent line. And that's what this formula represents. Okay, so that is the tangent line problem. And this really is, pretty much gives you the derivative. And in general, so in this case, the slope of the tangent line, that was dealing with a fixed point. And it's got fixed point C comma f of C. The difference is for derivative, it just is a variable change. So in general, for any x value for which this limit exists, the derivative of f at x is the following. And you'll notice that this is the exact same limit as this. It's just using the letter x instead of the letter c. They use the letter c as being a fixed value, and in this case, a specific fixed value, whereas in the derivative definition, x can be any x value that's on for the curve for the function f. So this will be used, and it's f of x plus h instead of f of c plus h, and then minus f of x instead of minus f of c over h, just like this is over h, and it's the limit h goes to 0. So that's the same. And then they use this symbols where it's got f and it looks like a quotation mark and then parentheses x. And this is read as f prime of x with the, looks like a quotation, single quotation mark. It's going to be called prime. So the f prime of x is how you say that. So f prime of x is the derivative, and it's equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. All right, and that's for all x in which this exists, and then the result, f prime, is a function of x. So the result is a function because you're dealing with any x, whereas the slope of a tangent line is dealing with a specific value, specific x value. In this case, they're letting the x value be represented by the letter c. And so the derivative, f prime of x, can give you the slope of the tangent line to f of x at any fixed x value. All right, and that's because they're pretty much the exact same formulas, just different, a variable change using x versus c. So yeah, if I find the derivative of a function, you can plug in whatever particular x value you're interested in, and that result gives you the slope of the tangent line of the curve at that specific x value. And some notations, and we'll be using this throughout the course interchangeably. The ones that we'll be using mainly are these. I probably won't use the last one. So I've already said what the first one is, f prime of x. So I said I've already talked about this one. The other one, where it has dy, looks like dy divided by dx. This really doesn't mean division. It's just a weird notation. And it's read as the derivative of y with respect to x. So sometimes they don't use, f of x. Sometimes they use the letter y to represent the same thing. All right, instead of having to write that function notation, we just use the letter y. And again, this doesn't mean dy divided by dx. It's a weird notation, does not mean division. It's just means you're taking the derivative of some function y with respect to x is what that means. And so the other one I'll be using a lot is the third one, where it has y, and that's y prime. That's just the derivative of y. All right, and again, y is the same thing as f of x. The fourth one is one I'll probably use the least amount, but it's d and then dx, and then in brackets is f of x, and it's read as taking the derivative of f of x with respect to x. And again, it does not mean division when it has d over dx. It just means take the derivative, and then you're specifically taking the derivative with respect to the variable x. Whatever's on the bottom part, that's going to be the variable which you're taking it respect to. And then in brackets that's the function itself. So you're taking the derivative of the function, in this case called f of x, with respect to the variable x. And I said all of these refer to the same thing. So yeah, all of these are referring to the same thing and will be used interchangeably throughout the semester. All right, that's just different notations you'll see, more so after this section, but since the book talks about this, I'll go ahead and mention these different notations. And the last one I probably will not even use. So the process of finding the derivative of f of x, so finding the, I forgot the words, the process of finding the derivative of f of x is called differentiation. So you might hear me say differentiation sometimes, in which case f of x is called differentiable if you can find the derivative. And that again, f prime of x is probably the one I'll use most of the time, along with y prime. So the process that we're going to be doing is called differentiation. And if the function has a derivative, then you say f of x, the function itself, is differentiable. And by process of finding the derivative, or the differentiation process, that's going to be applying this limit. Okay, so that's pretty much all of the main points, and now it's just going into examples. These first two examples are going to be finding the slope of a tangent line to the given function at the given point, which I would be applying this definition of slope of a tangent line at some point. All right, so that's where I'll stop this video. The next video is going to be going into specific examples. This was just meant to go over the main concepts.